Um, Hello everyone. In this video, I would like to show you a very simple demonstration of how to use the QAquifolium program to simulate very simple trapezoidal channel system. Um, so as you know, QAquifolium is a program, it's a very flexible framework that allows people to build uh, a wide variety of models of water systems, um, including or using components that they can design with completely user-made properties and governing equations. So it's every model is made of a network of something we call blocks or nodes and some edges connecting the nodes to each other. So essentially, what the blocks are, they are where we do some sort of material balance, including water balance, or we could do energy balance or pollutants and things like that. And then the connectors are somehow the interfaces between the blocks. Now these blocks can be they're built of some templates or that can be combined into plugins, and those templates or plugins can be added to the model. So what we have here is this the graphical user interface of QAquifolium. Actually, there's another version called Aquifolium, and that is essentially the API version. It works based on a scripting language, but then it's easier to use the graphical user interface, which is called QAquifolium. So I'm going to show you this. So essentially, what we have is that we have, if you look at the screen right now, this is the main window of the graphical user interface, and we have several default essentially blocks or nodes, and then we have connectors. Now these things, it's the model is under construction, so I expect these things to change and maybe some components to be added and some components maybe moved to external plugins. So we have a number of blocks. So for example, here we have a catchment. If you move your mouse on them, you're gonna see the name, and then we have some links. Okay, different link types. They have different governing equations controlling the flow of material into them. And then for optimization purpose, we have objective function and we have parameters, and then we can have sources. So sources are things that can, produce material, including, one thing is one source can be precipitation. If you want to model, build a rainfall runoff model, you gotta need precipitation. We can have other type of sources. Sources can essentially what the sources are. They can be connected to or they can be associated a time series or an equation that generates something that externally affects our system. Now, what I'm going to do is that in this video, I'm not going to go into the details of how to create plugins, but I'm going to use some plugins that have already been developed by me, and they are part of the installation package. So when you install QAquifolium, they should be copied onto your hard drive. So what I'm going to do is that I will have this plugin in this case called Open Channel, which currently has only trapezoidal channel, but I plan to add additional types of channels to it, including rectangular, maybe even curved cross sections and other things. So the first thing I'm going to do is that I will add this plugin. So if you take a look at these, the toolbar, you'll see these default kind of blocks that are present right now. What I'm going to do is that I will go to Preferences, and then I'll go to Add Plugin, and then I'll look for those plugins. They are saved in JSON files. It's a data structure that you can basically store object-oriented data in. So it's basically the default plugins are you can save your user main plugins anywhere you want, but in this case they are in a subfolder. I mean, the default plugins are in a subfolder called Resources. that are in the same folder that where Aquifolium is installed. So in Windows systems, when you use the distribution version to install the program, the plugins will go. The resources folder is where the program is installed, which is usually in this program files x86 folder. So what I'm going to do is that you see a number of different plugins. So the main components, these are the default ones that are already loaded. And if you see the log window right here, it says, when you start the program, it says this template called main components was successfully loaded, and that's why you see those, the default tool, essentially tool bottoms on your toolbar. What I'm going to do is that, so here we have an unsaturated soil for, the operations for water flow in unsaturated soil. But then the one that I'm going to use is open channel. So I'm going to click on open channel. I'm going to open it. And as you can see, some components were added to my this toolbar, including, we have a trapezoidal channel segment. And then we have some, so this one is the link from a channel segment to another channel segment. So this controls from the flow from one channel segment to another one. And then we have basically boundary condition. So this is if you have a fixed head boundary condition and you want to connect it to a channel segment. And then here we have a case when you have basically channel segment and you want to connect it to a fixed boundary condition. So essentially, this can be our upstream boundary condition, and this can be our downstream boundary condition in case the boundary conditions are fixed head. In this case, because I want to keep the example simple, I'm going to use these. But then you can also, for example, use a catchment to generate runoff and then divert that runoff into an open channel and so forth. So the first thing I'm going to do is that I'll create my channel. Then I'll do a few simulations. So the first thing, let's just add one trapezoidal channel segment. So what I'm going to do is that I will make each channel segment to be to have a length of, let's say, 10 meters and then a slope of 1/100. So we need to provide some properties. So if you select the component, this property window shows up where you can essentially select or specify the parameter values associated with this. And these parameters are all indicated in the JSON file that we opened. So in a future video, I'm gonna just open one of those JSON text files and then go line by line and explain what each of the what the structure of the file is. So anyways, we have this Manning's roughness coefficient. So I'm gonna just assign a value of 0.01. The initial storage is how much water is in this one segment of the trapezoidal channel. So I'm gonna just assign a number. Let's say we have 0.2 cubic meters. This hyphen height and width, these are really not important. These basically show the height and width of our the graphical component that you see on the screen. They have no effect on our simulation result. And in the future, I may just hide them because that will make things easier. And then we have a base width. Of course, that's the base width of the trapezoidal channel. So let's go with 1 meter. The bottom elevation, I'm going to keep it at 0. So that's the bottom elevation of the trapezoidal channel. So it's based on, you can do it based on the sea level or based on any kind of datum you want to do it. And in this case, I'm going to assume my, upstream trapezoidal channel segment has a bottom elevation of 0. The segment length, sometimes the name of these properties are not readable unless I basically expand this column. In which case, you can just move your mouse and you'll see the full name of the property in your tooltip. So basically the segment length, as I said, I'm going to make it 10. You have a side slope. So let's say this is a trapezoidal channel with a side slope of 1. And again, you have this x and y, and they are they show the location of the graphical item essentially here. So they don't have any. So if I move them, come back here, you'll see that they change, but they don't have any effect on our simulation results, so you don't have to be worried about them. So that's what I did. I created one trapezoidal channel segment, and I assigned the properties. Now what I'm going to do is that I want to populate. Let's say my channel is 50 meters. So what I'm going to do is that I will just copy this block 4 times, and I'll get my channel. So basically, let's do it. So I'm going to copy this, and then I'm going to paste. So I have a second one, which I'm going to put here, and I'm going to copy and paste, and I get another one, and I'm going to copy that one and paste, and I'm going to get the fourth one. Now let's move them here, and then the last one, I'm going to copy this and paste it, and here's what I'm going to get. So we have 5 of them. Now they're all identical. They have the same properties, and basically, by the way, something that I didn't mention is that you can change the name of each of these components the way you want. So if you have a name property that you can change, but in this case I want to just stick with the default names, which is essentially trapezoidal channel segment 1, trapezoidal channel segment 2, and so forth. Now what I want to do is that I want to keep all the properties of the channel segments the same, except for, because we have this slope downward, the bottom elevation of each of these trapezoidal channel segments are going to be different. So what I'm going to do is that I will just click on the second one, and if my slope is 1/100 or 0.01, that means if I move 10 meters ahead, I'm going to go down by 0.1 meter, right? So basically the bottom elevation of the second segment will be minus 0.1. The bottom elevation of the third segment will be minus 0.2. The bottom elevation of the fourth one will be minus 0.3. And then the bottom elevation of the last one will be minus 0.4. Okay, so the next thing I want to do is that I want to connect them. Now keep in mind that you can't really use any connector for any blocks. The connectors should match in the sense that the variables that they need in order to calculate the flow, they have to be available in the blocks that they connecting to each other. For example, in this case, usually you have a hydraulic head that is needed to calculate the flow, so basically the trapezoidal channel should have those. But in this case, for example, we also need cross-sectional area and things like that. These are calculated internally, and so we can actually calculate certain quantities in each of the blocks dynamically, and they are determined all in the plugin files. That's what I call, or template files to be open, and I'm gonna go over that in a different video. But anyways, for trapezoidal channel, they have these connectors. This connector is a link from a channel segment to another one. So I'm gonna click on that one, and I'm gonna connect each of the basically the channels sequentially to each other. So I'm gonna do that one, and then I'm gonna do another one, and then I'm gonna do here. Now if you click on the links, you'll see that they don't have any properties. So sometimes the links should have properties and we can assign them, but when I design the plugins, I'll try to minimize the properties of the links because of the fact that we can't really copy the links. So if you have a property, if the edges or the links had some properties, I needed to click on each of them one by one and assign those properties. And in this case, I don't have to do it because they don't have any properties directly associated with them. Now they have some hidden properties or dynamic properties that can be calculated, and I'm gonna later on talk about them. But they don't have any properties that needs to be asked from the user. And by the way, anything you do, you have this log window, and your actions are written, or if some errors happen or something, if I choose, for example, the wrong connector to connect 2 blocks, I'm gonna get an error here that's showing with red color, and I'll know that I've made a mistake. So basically this is what we have now. The model is not complete yet, but I can actually run it. I can run this model, and what I expect is that we have this 0.2 cubic meters of water in each of these elements. The units are not necessarily, they don't have to be SI units, but they they have to be just consistent with each other. So anyways, I have this one. Because this channel has a higher bottom elevation, I expect the water to flow down and then stays down here. Now I can provide. So if I go to settings, but anyway, this is an object browser, so I can actually see all my objects here too. So if I expand the blocks, you're gonna see these 5 channel segments, and if I click on connectors, you're gonna see these four connectors that are connecting with each other. They also have a settings branch, and essentially we can determine, or we can specify the simulation end time and the simulation start time. And so what I'm going to do is that I'm going to keep it here, but you can actually choose some real dates. You can say, run the model from, I don't know, January 1st, 2015 to December 31st, 2015, for example. Give some real dates, and that's useful for cases when, for example, we have some real data, for example, on climate data, or if you have some observed data that we want to calibrate the model with, and so forth. So what I'm going to so as I said, I can now run the simulation. Basically, you just go to this, the gentleman who's the icon of the gentleman who's running, and you can click on it, and basically the simulation is conducted. And what you can see is essentially here we have this is the runtime window. It shows we can see some information on the left hand side panel. Simulation started and ended. So this simulation was pretty simple. It took only 1 second. And now you could, sometimes the simulations may take longer if you have more complex systems and so on. You may decide to, I don't know, stop it in the middle of the run. You can see the progress here. And if I click on this one during the run time, I'm going to see some more details about how the simulation is being done. And then the graph that you see is actually the time step size. So this is QAquifolium is based on an adaptive time step scheme. So that the time step it can change, it can vary depending on the stiffness of the system of ordinary differential equations that are solved by the program. So in this case, the problem was actually ended up pretty simple after a very short period of time. So the time step just kept increasing. So I'm going to close this. Now, if I can now look at some of the results. So if I right click on each of these blocks, I'm going to see this item called results, and you see several items here. These are all defined in our template, so the user can decide what quantities to be calculated for each of the blocks or each of the types, and are shown in the output. So in this case, I decided to basically show these kind of results. So basically, the area of this is actually the cross-sectional area of the water flowing. You can have depth, head, perimeter, storage, and so forth. And for connectors, of course, we have other quantities. So if I click on a connector, you'll see, for some reason I put the Manning coefficient, even though it's always constant, but I wanted to do some debugs and so forth. But you have area, you have flow, you have hydraulic radius, length, and perimeter. So what I can do is, let's just right click and look at the storage. So if I look at the storage, surprisingly, what I'm going to see is essentially it looks like it's all zero. Now I can show you it's actually not. So you have the first time step. You have initially it starts from the storage of 0.2, which is the initial value that we provided, but it drops to 0 pretty quickly, and that's because the speed of water flow is way higher than our, or it's pretty large compared to our simulation time span. I can go ahead and maybe zoom in and get a little more detail. So you see that it takes some time, say some I don't know, minutes or so for the water to go to 0. Now eventually what we have is we should have all the water to gather in our last segment. So essentially, as you can see, eventually the water depth in our last channel, it goes up. Again, I can zoom in and see a little more details and so forth, but it happens really quickly. and all the water goes to our last channel. And you can look at the, for example, the flow here. So this is the flow again. It starts from a very large value at the beginning, and it went to zero as the channel elements started drawing out. So let's see. I'm just curious to see if any water left in the last. It's probably not, because what we have is that water depth here gets to point 0 something like 0.07 something, and we know that this channel segment is 0.1 meters below the one before the last one. So this channel also gets completely dried. I can change my initial condition and I get different results and so on. But I want to move on. So what I'm going to do right now is I want to, let me zoom out a little bit. I want to add some boundary conditions and reach to a steady state condition. So basically I'm going to use two fixed head boundaries. I'm going to put a fixed head boundary at the upstream boundary and a downstream boundary, and then I'm going to connect it, and I'm going to create a situation so we have a continuous flow. By the way, if you want to see more details about the flow, one thing we can do is that if you go to this solver settings, we can actually reduce our initial time step, and that will give us more details. Basically, that will make the program to choose smaller time steps, and we can see more details, the dynamic evolution of the water content in each of the components. So anyways, what I'm going to do is I will just add a fixed head boundary. So I'm going to basically place it here up, and I'm going to change the name, right, so that I can so let me make it a little bigger. So basically what I'm going to do is that I will just change the name to upstream boundary. And then I'm going to add another one. And for this one, I'm going to change the name to, let me zoom all. I'm going to change the name to downstream boundary. Okay, so and now if I go to my blocks, I'm going to see, or for some reason, okay. So I'm going to see this upstream boundary and downstream boundary added to my blocks, and then essentially what I'm going to do is that I will just add. So I need to use the right links. So I'm going to we have this link called link from a fixed head boundary to a channel segment. So I'm going to click on that one, and I'm going to connect that from here to here. And again, this link doesn't have any properties, so I don't have to be worried about assigning the properties. And then I'm going to choose this one, which is a link from a channel segment to a fixed head boundary, and I'm going to basically right there. So so now the other thing is that you can have, for fixed head boundary conditions, we can have some initial storage. We still keep track of the storage, how much water goes into them or goes out of them. But and it's important to have adequate amount of water, because if the water runs out in this fixed head boundary condition, there will be no flow afterwards. So things will basically stop. So I'm going to now put a very large, let's say 100,000, a very large initial storage value in the upper boundary condition, so that hopefully the system does not dry out. And then the other thing is that I need to, if it's the fixed head boundary condition, I have to specify the head. So what I'm going to do is that, let's say that I know the bottom elevation of the trapezoidal channel was 0. The upstream block of the channel was 0. So I'm going to go a little higher than that to make sure there will be flow. So I'm going to go with let's say a 0.05. Okay, so let's say the fixed head boundary, the head in the fixed head boundary condition is actually 0.05. And then I'm going to do here I don't have to be worried about the initial storage, because I know that flow is going to be this way, so this is not going to dry out. So what I'm going to do is that I'll just indicate a head, and let me see. So basically the bottom elevation of my bottom trapezoidal channel was -0.4, I can do this, maybe a little lower than that, but this is just an example. So let's go with 0.045. Okay. So now we have this thing set. I'm gonna save it again, and I'm gonna run it, and let's see what happens. So let's just run it, and so the first thing I want to see how much flow went out of my upper boundary. It can be a reservoir or anything. So I'm going to look at the storage, and as you can see, so this is how the storage of my upper boundary is going to change with time. I can, if I increase the duration of simulation, I'm going to see, what will happen in the future. But initially, if you have a high value for some reason, and then it slows down, I can look at the flow. So this is flow into our system. I can look at the flow, let's say, and you'll see that we have a high flow at the beginning, and then it'll go to a pretty small number. I'm not sure if that's exactly. It's not zero. It's a small value. So probably because anyways, you can look at the storage in each of the, or maybe water depth. If you look at the water depth is high, initially 0.02, and it goes down to a very small value. Okay, so the parameters are that I picked for the problem are a little strange, maybe. So that result in a kind of a small depth. Maybe the slope is too high. You can look at the flow here, for example. So let's say the flow it goes. Again, it's initially high, but it goes to something. Yeah, this is the unit of flow is cubic meters per day, so it's basically a little bit of flow. I don't know. Anyways, and then I can also look at the storage in the bottom reservoir, and as you can see, you have a high increase, and then it sort of flattens out. So that's pretty much it. I'll show you some other videos soon. Have a good day.